Hi everyone, in this video we are going to go through the first section of Chapter 4 titled Vector Spaces. In 4.1 we get an introduction to both vector spaces and subspaces. There's a lot, some of the slides on this section have a lot of words on them. I'm not going to just read them all out loud to you because that would make this god awful. But what I will do is say some of the important pieces on the slide. So however you're handling your note taking on these videos, my suggestion maybe would be to pause first, read through what's on the slide, and maybe you could take some notes down of what you think might be most important, and then maybe unpause and listen to my ramblings on and what I have to say about that slide. So at the beginning here, we get a definition for what is called a vector space. You have seen vectors before, hopefully in this class, but you've seen them in other classes. But now we're defining something different, a collection of vectors or objects in a vector space. And in order to be considered a vector space, these 10 axioms have to hold. They have to be true for that space. The axioms should be familiar, right? The vector addition commutes, so you have the associative property with vectors, scalars, and all that. Things that these axioms you have seen in one way or another previously, okay? And they apply to this thing that we're defining as a vector space. We can then move on to this next slide, and this next slide does not have much on it, but you could use those 10 axioms to prove these three fairly basic concepts that hopefully make sense. When you multiply a scalar of 0 times a vector, whoa, that was supposed to be an arrow. When you multiply a scalar of 0 times a vector, you produce the 0 vector. If you multiply any scalar times the 0 vector, you produce the 0 vector. And if you point a vector in the opposite direction, that's the same as multiplying a scalar of -1 times that vector. We're not going to go through proofs of how these can be formed from the 10 axioms, but it would be fairly straightforward to do so. All right. Now, the first example, again, these are wordy. There's not a lot of stuff to do in them. Read them, see if they make sense. These are all spaces that you've seen before. So exercises 1 through 5 discuss familiar spaces, terms, and why each of them is considered a vector space. That is, they satisfy the 10 axioms. Okay, and the first one is one that we've seen the most often in this course, and that is Rn. The space Rn is, they call it the premier example of vector spaces. The geometric intuition developed for R3 will help you understand and visualize many concepts throughout this chapter. Basically, R3, R4, R5, any ordered set of numbers satisfy the 10 axioms and is considered a vector space. That's what example 1 says. All right. Example 2, even if we look at the very visual application of vectors, so not just writing them down as numbers in a column, but the visual application of vectors, V, the set of all arrows in three-dimensional space with two arrows regarded as equal if they have the same length and point in the same direction. Read through the rest of this example. The set of arrows that point in directions is considered a vector space. Even if we don't assign numeric value to them, they still satisfy those 10 axioms, and we could show how they satisfy those 10 axioms, which is kind of cool. We're not going to, but they're considered a vector space, whether we write them with numbers or just consider them as arrows that point in directions. All right. Example 4, this is where we get into slightly more abstract mode. The set Pn of polynomials of degree at most n. So the set of polynomials, so P of t equals a0 plus a1t plus a2t squared all the way up to an t to the n, that is a vector space. Okay, the coefficients are real numbers. The degree of P, they say, is the highest power of t. It's a vector space. So even though we think of them as very separate topics, in this chapter we'll see how we can consider a polynomial just a vector written in a certain way. The first entry is the coefficient of t to the 0 power. The second entry is the coefficient of t to the first power, et cetera, et cetera. So these are, they're considered vectors. And again, read through the rest of this example and see how that makes sense a little bit. Example 5 is a set of functions. A vector space is the set of real-valued functions defined on a set D. So the set of functions is also considered a vector space. I can add functions together to produce functions. I can multiply a function times a scalar. Those 10 axioms from the first slide apply to the set of functions on a set D. Okay, again, that's a little bit more out there than just the set Rn. Okay, but functions satisfy those 10 axioms to be considered a vector space. Okay, so once we get the definition of vector space out of the way, now we can define what is called a subspace. So if I have a vector space V, a subspace is a part of that vector space. It's a subset H, it's a subset H of V that satisfies just 3 properties. And we'll spend more time figuring out what is and is not a subspace of a vector space. But it has to satisfy these 3 properties. It has to contain the 0 vector, has to be closed under vector addition. If I add vectors within my subspace, I produce vectors that are still within that subspace. And then it has to be closed under multiplication by scalars. If I multiply by a scalar c, I produce a vector that is still in that subspace. Okay, so that's what it means to be a subspace, and we'll spend some time looking at that. A fairly preliminary example of a subspace is this next example, the zero subspace. If I have a set that only contains the 0 vector in any vector space V, it is a subspace of V. So if you go back to the last slide, it checks off those three different pieces from that definition, the 3 different cases in the definition. Does the 0 subspace contain the 0 vector? Yep, there it is. If I add 2 vectors within that subspace, that is 0 plus 0, do I produce a 0 vector? Yep, I do. If I multiply any scalar times the 0 vector, do I produce a vector that's in that subspace? Yep, there it is. So the 0 subspace, while not very interesting, is a subspace of a vector space V. This next example is something that is specifically not a subspace. So they tell us the vector space R2 is not a subspace of R3, because R2 is not even a subset of R3, right? And the logic behind that is that vectors in R3 have 1, 2, 3 entries. Vectors in R2 have 1, 2 entries, right? So this thing can't be a subspace of that thing because they don't look the same, okay? But if I define my H here, if I define my H as ST0 having 3 entries, but still clearly looks like it's in R2, it's not in R2. It exists in 3 dimensions. It's the XY plane in a 3-dimensional space. It's a subset of R3 that looks and acts like R2, but is distinct, different. It is not R2 because it has 3 entries. Okay, but here's where we have to do a little bit of work. Show that H is a subspace of R3. So how do we show something is a subspace? That's what we're going to look at with this example. Okay, so we need to show that it checks off 1, 2, 3 different boxes. One being that it contains the 0 vector. Okay, so how do we do that? All right, we should say H, which is ST0. What if S and T are both 0? Well, then what does that vector look like? 0, 0, 0. Oh, okay. So it contains the 0 vector. Check that off. That's 1. Okay. 2, we need to show that it's closed under addition. Under addition. Okay, so how do we do that? Well, we're going to define a vector U, and that is S1, T1, 0, and a vector V, that is S2, T2, 0. Okay, and then I say, all right, well, what is u plus v? How do I add those two vectors together? Add the corresponding entries, just like we've done previously. S1 plus S2, T1 plus T2, and 0 plus 0. Okay, and then the last thing we'll say, which is in H. And how do I know it's in H? Well, because it has an entry that's a real number, it has a second entry that's a real number, and a third entry that's 0. So clearly it's in H. I didn't say it with step 1, but I just kind of wrote a check mark. That's in H because 0 and 0 are both real numbers. All right. Now, for the third piece, we got to show that it's closed under scalar multiplication. Okay, so how do I do that? I'm going to say, all right, I've got u is equal to s and t and 0. So then what is c times u for some scalar c? Well, it's cs, ct, and 0, which I know is in H. And how do I know it's in H? Well, because this entry is a real number, this entry is a real number, and 0 stayed a 0 when I multiplied it by that scalar. Okay, so those are the steps to show that something is a subspace. All right, now moving on to example 10, we have two vectors, v1, v2, and h is defined as their span. The span of v1, v2, we have to show that h is a subspace of the vector space V. Okay, and we go through the same three steps as the previous example, but this one is maybe a little bit more abstract. I mean, it's talking about span. It requires that you remember what span is, right? It's a set of linear combinations of V1 and V2. That's how we defined span previously. So how do I show that the 0 vector is in there? Well, I can produce the 0 vector by taking a scalar of 0 times V1 and a scalar of 0 times V2. Well, there we go. That shows that the 0 vector is in H. Okay, if both of my scalars are 0. All right, the next one is a little bit more work. We have to define two vectors. So we let u equal s1 v1 plus s2 v2 for scalars s1 and s2, and v is going to equal what did I use there? Actually, no, I didn't use v because this problem already has v's in it. So let's change that to a different letter, w, okay, because, again, the problem already has v's in it. W is equal to t1 v1 plus t2 v2. So those are my two arbitrary vectors that I'm defining in this vector space H. And what I need to do is now add them together. Well, then u plus w is equal to, now I could just write them again. Well, no, I will actually write them again for this step. So that is s1 v1 plus s2 v2 plus t1 v1 plus t2, whoops, not 2t, plus t2 v2. All right, so I'm adding them together, and now I can rearrange and regroup things to show that S1 plus T1 times V1 plus S2 plus T2 times V2 is what I get when I add U and W together. Okay, so think about how you would have to rearrange that. Put the V1s next to each other and then factor them out. Put the V2s next to each other and then factor them out. And how does that show that it's closed under vector addition? Well, I've added two vectors that look like they're in H, and I've produced a vector that looks like it's in H, right? S1 plus T1 is my scalar times V1. S2 plus T2 is my scalar times V2. So I'll say which is in H. That sum is in my space H. Okay, so we've got closed under addition. The last piece here, we've got to show that we're closed under scalar multiplication. So I'm going to say given scalar C what is C times U equal to? Well, it's C times S1V1 plus S2V2. And I can rearrange, regroup, and all that to show that this is CS1V1 plus CS2V2. The S there is not a subscript; it's a regular S, and that is clearly, hopefully, you can tell this is a linear combination of V1 and V2. So which is in H? I know that that's in H because that's how H is defined. Okay, so then the conclusion of this example will say 3 dots for therefore H is a subspace of the vector space V. Okay, so there's 2 examples where we show that's how we show that something is a subspace of a vector space. All right, and then we get to a theorem, and our theorem says that if I have a set of vectors, we are not going to do a proof of this theorem, by the way, but if I have a set of vectors, they're V1 through Vp in a vector space V, then their span, the span of that set, is a subspace of V. Okay, so if I'm talking about span within a problem, I can just refer back to this theorem that says that the span of a set of vectors is a subspace of V. Or if I can show that something is spanned by a set, if I can write it as that linear combination that we did that we were given in the last example. Okay, and that's what we'll see in the next example. Okay, so example 11, let H be the set of all vectors that have this specific form here, and A and B are arbitrary scalars, and then we define H that way, or that is H. Show that H is a subspace of R4. Okay, so what we will do first here is we're going to take that the way that we're given H, written horizontally as that coordinate is not helpful to what our goal is here, to being able to see it as clearly as possible. So I'm going to take those 4 entries. You might not have even noticed there's 4 entries in H, but it tells me we're in R4. And I'm going to write them vertically. So the first entry is A minus 3B. The second entry is B minus A. The third entry is A, and the fourth entry is B. And what we can do is we can first split this up into 2 vectors, one containing all the A entries and one containing the B entries. So the first vector here is A, negative A, and 0. And then the second vector is negative 3B, positive B, 0, and B. And in doing that, now I can factor an A out of that first vector, 1 minus 1, 1, 0. And I can factor a B out of the second vector, minus 3, 1, 0, and 1. That's a 0. And now, hey, I've got a linear combination of those 2 vectors. So if I call this guy V1 and this one V, not 1 again, V2, now I can say this shows that H is the span of the vectors V1 and V2. That's a 1. And by theorem 1, the one from the last slide, is a subspace of R4. Done. So that's that theorem saves us some time. I could have gone through the exact same 3 steps as I did in the previous 2 examples. Show that it contains a 0 vector. That wouldn't be terrible. Show that it's closed under vector addition. That would take a little bit of work. And show that it's closed under scalar multiplication. A little bit more work. Effort, writing. But if I can show that it looks like that we have the span of a set of vectors, poof, done, using the theorem. Okay? Now, the last example says, for what values of H will Y be in the subspace of R3 spanned by those 3 vectors, if this is what all of my vectors look like? Now, the wording of this question should sound a little bit familiar because actually, in section, let's see which one it was, 1.3, problem number 2, or example number 2, or practice problem number 2. This was a problem from a previous section. The only thing that's different, like the exact problem verbatim, the only thing that's different in this example, in this chapter, we have the word subspace, and in the previous section, that word was replaced with span, is spanned by that set. And so like those two topics very much overlap here in this context, and I think the answer that we got from that in that example was that it's in the span if and only if h is equal to 5, and we got that by augmenting and doing row operations. Okay, and so that same context from the previous chapter, we can use here just with this new word that we've been introduced to. Y is in the subspace spanned by those three vectors. They very much overlap in how they work. Okay, so that's a very anticlimactic end to the section. This is a similar problem to one we did already, but it is, and so the topics overlap here as we go through things. Okay, but that's the end of section 4.1. If you have questions, please email me, let me know, and good. Thanks for watching.